So this is the fourth lecture on advanced course in classical logic. Today we continue discussing the infinitary classical propositional logic and consider the main question for any logic. How can we build axioms and prove completeness of these axioms and rules? On the previous lecture, we already wrote the axioms and the rules, and today we will show that they are complete in some sense, but not in the the strongest sense that we wanted. So we have a language with countable conjunctions and disjunctions, and with a countable set of variables. So we have two cardinals that are parameters of our language. Everything in this lecture can be considered for other cardinals, but there are some for greater cardinals. There are some difficulties in building axioms, in proving completeness, and even some statements become false. Some completeness, compactness, and other statements become false. Okay, so just a reminder, we build formulas from variables using negation and at most countable conjunction. If phi is that most countable set of formulas, then conjunction phi is a formula. And we can define countable disjunction by De Morgan law. And we consider Boolean semantics or two-valued semantics. To each variable, we assign a valuation. To each variable, we assign a 0 and 1. So this assignment is called evaluation. We use this notation for the formula A is true under V. And we extend this valuation from variables to all formulas by usual clauses. So negation is true if the formula is false, conjunction is true if all formulas are true, and of course disjunction will be true if some formula from phi is true. Of course, this last line is a consequence of the first two, because disjunction is not a primitive symbol but a defined symbol. So a tautology is a formula that is true for all valuations. A satisfiable formula is true for some valuation. And we say that a set of formulas is satisfiable if it is true for some valuation. All formulas from gamma are true for some valuation V. Okay. In the previous lecture, we already saw these axioms and rules. So axioms, we simply write all tautologies for the usual conjunction, disjunction, implication. Of course, we can express binary conjunction from this infinitary conjunction, and all other connectives are expressible as well. So in the first axiom are tautologies for these finitary connectives. And now we have a schema. So if A is a formula and phi is a at most countable set of formulas which contains our formula A, then this is an axiom. Rules, modus ponens. If we have A and B, then we derive B. And the following rule with infinitely many premises. If we have already derived implications A implies B for all formulas B from phi, then the next step, at the next step, we are allowed to derive this formula A implies conjunction phi. This rule resembles the Bernoulli's rule from classical propositional logic, from classical predicate logic, sorry, for quantifiers. A implies B of X, A implies for all X, B of X. So this is very similar. Okay, we already introduced the notion of a derivation or a proof. A derivation is an at most countable sequence of formulas. So our sequences will be indexed by ordinals. In the usual logic, we have a finite sequence. Here we will have not only infinite sequence A0, A1, A2, and so on, but we will have sequences ordered by ordinals. So A omega plus 1, A omega plus 2, A omega plus omega, and so on. So proofs may be rather long, omega times omega, and so on. But at most countable. Why we do this restriction, we will discuss it later. It is an important thing. So a derivation or a proof is an at most countable sequence of formulas indexed by ordinals, such that each formula is either an axiom or is obtained from previous formulas by some rule of inference. We have two rules. One requires just two formulas before it. This rule requires infinitely many formulas before it in the proof. So if a formula is derivable, we write this symbol. Provable or derivable, or is a theorem of this calculus, of this logic. Of course, we can similarly introduce the notion a formula A is derivable from a set of formulas, gamma. In this context, gamma is called the formulas from gamma are called hypotheses. And again, here we introduce this notion only for countable sets. We will discuss it later. Why only for countable? Uh, so this notion means that there is a derivation such that each formula in this derivation is either an axiom or an element of gamma, or is obtained from previous by some rule, and the last formula is A. So like in the usual logic. Here's an example. If we have some at most countable set of formulas, then from this set of premises of hypotheses, we can derive this formula conjunction phi. Indeed, let us consider this derivation. Let us fix some tautology. For example, P implies P, or just top, or P implies top, any tautology that you like. Then we write the following derivation. Firstly, we write, so let us assume that phi is indeed countable. It may be either finite or countable. For finite sets, this is a trivial statement, so already known from the usual logic. So let us assume that phi is a countable set. So firstly, we write all formulas from phi, A1, A0, A1, A2, and so on. So we have already omega steps in our derivation. We have written already countably many formulas. Next, we write this, the formula of this form, A implies D implies A, for every formula A from phi. So again, we have omega steps here. So our derivation has already omega plus omega steps. Next, we apply modus ponens to these two and write these formulas. D implies A. Again, we have omega formulas here. So we have 3 omegas already. Next, we write this formula. D implies conjunction phi. It is obtained from these infinitely many formulas by our rule of conjunction. We have already infinitely many formulas of the form D implies A. So we can apply the rule and obtain this formula. Then we write D. It is a tautology, so it is an axiom of our logic. And then by modus ponens, we obtain this conjunction phi. So the length, so the formulas in this derivation are ordered as omega plus omega plus omega plus 3. can we write a shorter proof? Of course, the proof will be infinite. It will have countably many formulas, but the formulas will be reordered so that the ordinal will be smaller. Can we do this? So here we have a, so this line, and this line denote omega plus omega formulas. Can we reorder them so that we use only omega steps? Well, in fact, we can firstly write, for example, phi is a0, a1, a2, and so on. It is a countable set. We can write a0, then a0 implies d implies a0. This is the formula number 2. Then d implies a0. This is the formula number 3. Then the formula number 4 will be a1, and similarly for a1. So we have 3 plus 3 formulas, and so on. So we reorder these formulas. So we have 3 plus 3 plus 3 plus 3, and so on. So these 3 lines will occupy only omega formulas. They will be ordered like the ordinal omega. And then we have step omega plus 1, omega plus 2, omega plus 3. So the same the same derivability can be shown by a derivation of omega plus 3 steps. And of course, we cannot do this better. We must have omega steps, of course. And the last 3 steps are seemingly is essential. We need them. We can't remove anything here. Okay, so this is an example of an infinite proof, an infinite derivation. As in the usual logic, we can prove deduction theorem, but now it has 2 forms. The first form is the usual one. If we can prove some formula B from a formula A and some hypothesis, then we can derive the implication A implies B from the hypothesis gamma. So we can move one hypothesis A into the premise of the implication. The form 2 makes the same trick, but with a countable set of premises, countable set of hypotheses. We can move a countable set of hypotheses here into implication by taking the infinite conjunction. And in fact, this line 2, this statement 2, is not much harder than 1. It simply follows trivially from 1. Because firstly, we know that we have an axiom, conjunction phi implies A, where A is a member of phi. So therefore, we can derive using modern exponents from this formula, conjunction phi, this formula A. So this is a trivial fact. Now let us use it. So assume that we already know 1, how to prove 2. Assume that gamma phi derives some formula B. Then from gamma and conjunction phi, we can also derive B, because firstly we can derive all formulas from phi, and then from them and gamma derive B. So using this trivial fact, we obtain this. And then we use 1, because conjunction phi is just one formula. We can put it into the conclusion, into the premise of the implication. So item 2 is a simple consequence of item 1. Well, item 1 is proved in almost the same way as for classical propositional logic. We only need to consider the new thing, our new rule that has infinitely many premises, the rule for conjunction. We will not go into details. They are written in the lecture notes. But now let us come to the interesting question. We defined derivations only for countable ordinals. Why do we consider only countable derivations? Maybe if we consider uncountable derivations, uncountably long derivations, then we can prove something new. It turns out that no, we cannot prove anything new. Everything that can be proved with countable derivation. So any provable formula has a proof of a countable length. And if A is provable from some gamma, then A has a countable derivation of from gamma. So this line says about just derivations from our axioms, just provable formulas. So any tautology in our logic can be proved from these axioms in at most countable number of steps. Well, when we prove completeness, of course. If we prove completeness, then we will know that every tautology can be proved in countably many steps. And here we say the same for derivability from hypothesis. Okay, why is this? Why countable derivations are enough? Let us derive consequences from gamma step by step. So first we start with formulas from gamma. And next we apply modus ponens to all formulas from gamma and our axioms. And to and the rule of conjunction to all formulas from gamma and our axioms. So at the next step, lambda plus 1, we take previous formulas and apply modus ponens and the rule of conjunction to all previous formulas. And for limit ordinals, we simply take the union of all formulas that we already obtained. So this notation apply rule means that we apply this rule R in all possible ways to formulas from gamma. It should be gamma here. It should be delta here, not FM. So all formulas that can be obtained from some formulas from delta using rule. And the main fact is that for any set gamma, so the question is, when do we obtain all consequences of gamma, all derivable formulas? For which ordinal do we obtain it? And the answer is, again, the same as in the previous lecture for some different question. At the step omega 1. Omega 1 is the first uncountable ordinal. So all ordinals before, all ordinals that are less than omega 1 are countable. And this is the first uncountable one, uncountable ordinal. So the lemma states that gamma omega 1 is closed under these rules. So if we apply rules of modus ponens and conjunction, then we do not obtain anything new. And this is not about derivations and infinitary logic and so on. We already saw a statement like this for building formulas, not proving them, but simply building formulas. This is a rather general fact. So if we have an arbitrary set X and we have an arbitrary set S of functions on X, but functions that can have 1, 2, 3 arguments and even infinitely many arguments, but only at most countable number of arguments. And moreover, we will consider even functions that are partial. They may be undefined for some elements of X. We already know examples of functions like this. For example, modus ponens. In fact, it is a rule of inference. A implies B, B. So it is applied to a pair of formulas, A implies B. These are two formulas. And it returns just one formula, B. And of course, this rule cannot be applied to any two formulas, C and D. We must have that D is an implication of the form C implies something, some E. So this is a function, but only partial function, and it has two arguments. Similarly, our rule of conjunction has omega arguments, and again, it is a partial function. It is only applicable to a set of formulas of the form A implies B, where B is any formula from some set phi, some countable set phi. And if all formulas are of this kind, we produce a formula A implies conjunction phi. So it is a function, but only partial function, and it has omega arguments. So our rules are special cases of this set of functions. Now, like in the previous slide, let us apply these functions to the set. So if we have some subset of X, then its image for the function phi, for the function f, is the set of all values where its arguments are from the set y. And image for the family of functions is the union of all images for f. Now, like in the previous slide, we apply these functions. It should be some. It should be not x, but some subset y of x, because if we apply our functions to x, we again obtain x. We cannot go beyond x, of course. So it should be y here. It is a typo. It's a misprint. So we start with some subset of x, and then apply all functions. At the next step, we take all previous the previous set, so all previous points, and new points obtained by all functions. And for limit ordinals, we obtain, we take simply the union. And again, it should be y, the set y here. For any set y, at the step omega 1, we obtain a set that is closed under all functions from our family S. This is exactly the statement for this previous slide about the rules modus ponens and the rule of conjunction. So here I just copied some pieces. So we define these layers. Again, it should be y here. So the main conclusion is that if we have only functions with at most countable set of arguments, then the closure is reached at the step omega 1, the first uncountable ordinal. Well, again, we already saw this proof in the previous lecture. So let us repeat it in this abstract form. So let us take any tuple of elements, infinite sequence of elements from the set X omega 1. So omega 1 is a limit ordinal. So each element AI belongs to some layer X lambda I for some lambda I which is smaller than omega 1. So if it is smaller, then it is a countable ordinal. Now, we can take the maximum of all these ordinals, but in set theory it is called not a maximal but a supremum, which is the smallest ordinal that is bigger than that's greater than all these ordinals. And then we obtain that all these elements are in this set X lambda. So this is a tuple of elements, a sequence of elements from X lambda. But then if we apply our function, we obtain an element from the next step, lambda plus 1. Therefore, this element is in the set X omega, because lambda plus 1 is contained in omega. Because if lambda is countable, lambda plus 1 is a countable. So the main thing is here that the supremum of a countably many of countable ordinals is countable again. Just as an analog countable union of countable sets is countable. So this is the main property of countable ordinals that we used. So our set is indeed closed under the function f. So the conclusion is that we don't need longer derivations. We only need countable derivations. So we state this completeness theorem. So our axiomatic system, the axioms and the rules, are complete in the following sense. A formula is provable if and only if it is valid. A formula A is derivable from a set of hypotheses gamma if and only if it follows from gamma. So this means that for any evaluation V, if gamma is true under V, then A is true. If all formulas from gamma obtain the value 1, then V of A is 1. And again, this item B is formulated for countable sets gamma only. We can notice that we do not need to prove B separately. In the usual logic, the second line is called strong completeness. And we usually need to, so some logics are complete in the sense of A, but not strongly complete in the sense of B. But here in the infinitary logic, B is just an easy consequence of A. Indeed, assume we can derive A from gamma. Then we can derive A from the formula conjunction gamma. By deduction theorem, we can move this conjunction gamma here and obtain the formula conjunction gamma implies A is derivable in our calculus. By item A, this holds if and only if this formula conjunction gamma implies A is a tautology, is valid. And then we easily obtain that from gamma we obtain A. It's just an easy equivalence. So for the infinitary logic, we do not have a difference between completeness and strong completeness. But the only thing is that here gamma is at most countable. We will discuss later why it is only formulated for countable gammas. This is an easy consequence of this previous slide that derivations are at most countable. Okay, but let us see how the completeness is proved for the infinitary logic. There are some new things and some difficulties. Usually we do the following. If some formula A is not provable, then it is contained in some. So the negation A is a consistent set. Then it is contained in some maximal consistent set of formulas. And then we show that any maximal consistent set of formulas is satisfiable. We can assign evaluation. So the variable p is true if and only if it is in this set. Here we cannot do like this. Because in the usual logic, we were able to build maximal consistent set by using Lindenbaum lemma. Every consistent set is contained in some maximal consistent set. We add the formulas one by one and obtain, and then take the union and obtain the consistent set. In the infinitary logic, this doesn't work because we have incompactness. We have some set of formulas such that every finite subset is consistent, but the whole set, so the union of these finite sets, is inconsistent. So the Lindenbaum lemma doesn't work, and we need to invent a new trick. So this definition of a consistent set is a straightforward generalization of the usual one. But now we can take in countable conjunctions. So it is easier to formulate. So a set of formulas, at most countable set of formulas, gamma, is called consistent if we cannot prove false from this formula, from these formulas, or equivalently. So by the deduction theorem, it is the same as saying that conjunction gamma implies bottom is not provable, or equivalently, not conjunction gamma is provable. So these are just equivalent definitions. And we will prove some analog of Lindenbaum lemma. Any consistent set of formulas is contained in some saturated set. It will not be the maximal consistent set. We will only build some small set H that contains gamma, and it is good in some sense. It is saturated. It is closed under some natural operations, but it doesn't have to contain for any formula A either A or not A. If gamma is countable, then our set H will be countable too. And the second step, any saturated set, in particular this set H, is satisfiable. So if we already know that we have proved these lemmas 1 and 2, then the proof of the completeness is as usual. So assume that A is not provable, then the set negation A is consistent. Consistent means that we cannot prove in our logic negation of this formula. But negation of A is equivalent to A. So we cannot prove A. We already assumed that we cannot prove A. So this is a consistent set. Then by lemma 1, it is contained in some saturated set H. And by lemma 2, H is satisfiable. So negation A is satisfiable in particular. So there is evaluation for which negation A is has the value 1. So A has the value 0. So A is not a valid formula. So this proof is the standard one. So we only need to give the definition what is a saturated set and why every consistent set is contained in some saturated set and why every saturated set is satisfiable. Where is the trick? So the trick is in this definition of saturated sets. So a set of formulas is called saturated. It is also called a Hinticke set in literature. If we have the following conditions, this set is consistent in the following sense. It doesn't have two opposite formulas. There is no formula A for which A and not A are in our set. And then we formulate conditions. If some formula is in our set, then some smaller parts, even smaller parts, are in H, not bigger. So if not A is in our H, then A is in H, but not vice versa. We only simplify formulas and state that these formulas are in H. We do not build bigger and bigger formulas. And this will help us to say that H is countable. Next, if our set contains this formula, conjunction phi is at most countable, then our set must have all formulas from this set phi. So phi is a subset of H. Like in the usual logic, if A and B is in the set, then A is in the set and B is in the set. But only one implication, from left to right. We don't claim that if H has all these formulas, then H has this conjunction. The conjunction may be much bigger, much longer than any formulas from H. So we don't claim that it is in H. So only from left to right, if, then. And similarly for disjunction, but we do not have disjunction in our language. We could introduce disjunction in our language and add some new axioms, but we can do the following. If negation of conjunction phi is in H, so this is something like a disjunction, then we must have at least one disjunct. But in this case, a disjunct is just some formula H, some formula not A. So if disjunction is in H, then some formula from disjunction is in H. But we formulate this in this negated form because we do not have disjunction. So our aim will be, given a set of formulas gamma, to build a saturated set that contains gamma. And gamma is at most, we will start with at most countable sets. And we will proceed as follows. We take gamma, then take all its subformulas, and then build the set H from its subformulas. The question is, if gamma is a countable set, what is the cardinality of this set? The set of all subformulas. Is it countable again? In the usual logic, if A is a formula, then the set of all subsets is finite. If gamma is a finite set of formulas, then the set of all subformulas from gamma is a finite set. But here, if gamma is countable, is the set of all subformulas countable?
Well, I think yes, because for each formula, a subset of all subformulas is also at most countable, I think. And countable union of countable sets is again a countable set.
Yes, so gamma is countable. So we need to simply investigate what is the set of all subformulas of just one formula A. And even though our formulas may be very, very long, the set of all subformulas of a given formula A is countable. So let us recall the definition. We didn't give the definition, of course, but one can easily give this definition of subformulas. The set of subformulas of P is a variable, it's just P, the set of P. The subformulas of negation is just this, the formula negation A itself and subformulas of A. And if we have a formula of this kind, conjunction, we simply take this formula itself and then take all subformulas of formulas from phi. For every A, we take subformulas of A. So by induction on the construction of formula A, we can easily prove that this set is countable. So we start with countable, with even finite sets. Here we obtain only one formula, and here we obtain countable sets. We take the union over a countable set phi. Phi is countable. And therefore, so this, strictly speaking, this is a proof by a transfinite induction. And then we obtain that for any at most countable set of formulas, the set of all subformulas is again at most countable. And now we are ready to build a saturated set. So we take as a consistent set at most countable set of formulas gamma. We take all subformulas and all negations of subformulas. So it is countable set. So we can enumerate formulas. I wrote it 2 times. We enumerate these formulas by natural numbers, a0, a1, and a2. In the usual Lindenbaum lemma, we build a tower of sets, gamma 0, gamma 1, gamma 2, and so on, by simply either adding a formula an or not, or we do not add anything, or in other variants we add not a n. But here we will need some additional trick, because the trivial procedure, the trivial method doesn't work if we have negation conjunction variables. So let us consider phi the set of variables. So negation conjunction phi. And then we add formulas P0, P1, P2, P3. At every finite step, we obtain a consistent set. But if we take the union of all these steps, we obtain an inconsistent set. So we can't do like this. We need some additional tricks. The trick is that we will build a sequence of formulas, sequence of sets of formulas. So gamma 0, gamma 1, gamma 2. And we have some intermediate steps, delta 1, delta 2, delta 3, and so on. All these sets will be at most countable. We will now show how to build them. And then after this, we take the union. Of course, the union of gammas is the same as the union of deltas, because every gamma is contained in some delta, and every delta is contained in some gamma. So the union will be our saturated set. This will be not very hard to show. So the only thing is how to build these formulas, these sets of formulas. So if we are at the step gamma n, so we build the gamma n, we build the next step, delta n. In the usual way, we put a formula an in our set if this new set is a consistent set. So our logic cannot prove the negation of conjunction of this set. But if it is inconsistent, then we do not add this formula and simply put gamma n. And now we need to make a trick for this negated conjunctions, because otherwise we can easily obtain an inconsistent set, which is not what we want. Next, from delta n to gamma n plus 1. If this formula an is not of the form negation conjunction phi, then we do nothing. We simply put the next set gamma n plus 1 is just our set delta n. If an is of this form negation conjunction phi, and this definition worked for the first line, so we really added this formula an to our set and obtained delta n. So if we added this formula, if we put this formula negation conjunction phi to our set, then we also need to guarantee that this intuitively disjunction has a witness, has some formula that guarantees that our disjunction is true. What does it mean? We need to find in our set of formulas phi some formula B such that this set, such that we can add node B in our set and still obtain a consistent set. The question is, why does this formula B exist? Okay, so we had some set gamma n, then we add this formula, not conjunction phi, and obtain a consistent set. The question is why there exists a formula B such that if we also add node B to our set, then we obtain a consistent set again. And this is guaranteed by our rule with infinitely many formulas. We can reason by contradiction. Assume that all these sets, for every formula B, all these sets are inconsistent. This means that our logic proves conjunction delta n implies B for every formula B. Then we apply our rule and obtain that our logic proves conjunction delta n implies conjunction phi. And then we easily see that this set delta n is inconsistent because it has already this formula, not conjunction phi, and we proved conjunction phi. So from this set we can prove not conjunction phi because it is just contained, and conjunction phi because we just proved it. So this is a technical thing, and this guarantees that every infinitary disjunction has a witness, has a formula that shows that this disjunction is true in some sense. Well, this is the main trick that was invented for the completeness proof of the infinitary logic. Now, the details are written in the lecture notes. So let us see the main idea of the lemma 2. In the classical predicate logic, lemmas of this kind are called model existence lemma because here we build some model, some set W with some predicates, functions, and so on. In our logic, we don't have predicates, functions, and so on. But by tradition, lemma of this kind is called a model existence lemma. In fact, we will build not a model, but just a valuation, just one assignment of zeros and ones to variables. So assume that H is a saturated set. We prove that there is a valuation that makes this set true. All formulas from H will be 1. The valuation will be as follows. We make a variable P true if and only if it belongs to this set H. Now we need to prove that not only variables from H are true, but also all formulas from H are true. In other words, for every formula A in H, we prove that it is true. Notice that in the usual logic, we prove an equivalence. A formula A belongs to our maximal consistent set if and only if this valuation makes it gives the value 1. But here we prove only one implication. Of course, we will not be able to prove that every formula that is true belongs to our H, because our H has only countably many formulas, and there are continuum many formulas that are true. For any evaluation V, there are continuum many. So 1/2 of formulas are true and 1/2 of formulas are false. So we cannot prove the converse implication. So we will prove only one implication. And what is the main thing that happens in this lemma? How do we usually prove something? For any formula A, something holds. We prove this by induction on the set of on the construction of a formula. Here we'll prove this by induction, but not on the construction of a formula, but a slightly different relation. So usually we prove by induction, by transfinite induction, for example, on the relation A is a subformula of B. Here we will need to change this relation. A is simpler than B. What does it mean? So we copy two items from the definition of a subformula. So A is a subformula of not A. So A is simpler than A. B is a subformula of conjunction phi. And we will say that B is simpler than A. But additionally, if we have not conjunction phi, we will say that not B is simpler. It is not a subformula, of course. Only B is a subformula. But we can introduce this notion, not B is simpler than phi. And this, like the usual relation A is a subformula of B, that relation is well-founded. So we can carry out transfinite induction on that relation. And this relation is again well-founded. And we can carry out transfinite induction on this relation. So we will build this statement. If A is in H, then its value is 1. By the transfinite induction on this relation simpler. And for example, if we consider the formula not conjunction phi as an induction step, then as an induction hypothesis, we will use some statement about not B. Not about the formula B, but not B, which is not a subformula. This is why we introduce this additional notion. Perhaps if we introduce the infinitary disjunction in our language and write the corresponding axioms to our calculus and the corresponding rule of disjunction, and we transform every formula into the negated normal form, then perhaps we can avoid this new notion in this proof. We could simply prove this statement by induction on the construction of the formula A. But here, since we did not introduce disjunction, we do like this. So, of course, there are some technical details in the proof, in this proof by induction. It is not very straightforward. There are some subtleties. So you can see them in the lecture notes. And the final comment. So we let us look at the completeness theorem. A formula is provable if and only if it is valid. A formula is provable from gamma if and only if it follows semantically from gamma, where gamma is at most countable. This item B cannot be generalized to uncountable sets gamma. And moreover, we cannot extend our logic by adding new rules of inference, but rules that have only countably many premises, so that the new calculus will be complete for all sets gamma. It is impossible to do this only for rules with countable number of premises. So we will, if we want this completeness, a stronger completeness, we need rules with uncountably many premises. Why this item B does not hold for uncountable sets? Recall that on the previous lecture, we had a set of formulas gamma such that every countable subset of gamma is satisfiable, but the whole set gamma is not satisfiable. Then, of course, since gamma is not satisfiable, it implies bottom. It implies false. For every evaluation that makes all formulas from gamma true, but there is no evaluation of this kind, false is also becomes 1. So there is no evaluation that makes gamma true. Then, if we were able to prove this completeness, a strong, very strong completeness, then we could obtain that gamma, from gamma we can derive false, but it is impossible because false is not derivable from gamma, because if it were derivable, then that false must have a countable derivation from gamma. But a countable derivation uses only countably many countably many formulas from gamma, some subset gamma prime. So gamma prime derives bottom, and then gamma prime implies bottom. But we know that gamma prime does not imply bottom, because any countable subset is satisfiable. So there are evaluations that make gamma prime true. And therefore, this countable subset does not imply semantically bottom. So if we want a very strong completeness theorem, it is not enough to consider rules of inference that have countably many premises. We need much stronger rules with uncountably many premises. So that's the end of the lecture. We can discuss some other questions.